Good day, everyone. So last meeting we had the properties of the limits of a function. So now we go to the limits in indeterminate form. So supposing we have this function x minus 1, okay, x minus 1 all over x squared minus 1 as x, or we get the limit of this function as x approaches 1. So using the properties we discussed last meeting, so we solve for the limit. Okay, so using property number, I think it's number 7. So we get first the limit of x minus 1 and then divide it by the limit of the 1 in the denominator. So x squared minus 1, okay, as x approaches 1. So limit of x minus 1. So let me put parenthesis. So limit of x as x approaches 1 is 1, right? Minus the limit of 1 as x approaches 1 is also 1. And then for the denominator, so we have limit of x squared. So meaning we get the limit of x as x approaches 1, then we square it. So that's 1 squared or just 1. Okay, and then minus limit of 1 as x approaches 1 is also 1. So we get 0 over 0. 0 over 0 means indeterminate. So it doesn't necessarily mean that there's no limit. It's just that it's not determined using using the properties, okay, of limits using this method. Okay, so let me show a graph of the given function and let's see if there's really, I mean, if there's a limit or there's none. So it looks like this. Okay, for a moment. Okay. So as you can see on the screen right now, okay. So the sketch of the graph of the given function is the green one. So it says as x approaches 1, so this is the x equals 1. So we have here this point. Okay. So as you can see from the right side, the function is getting closer and closer to that point. And from the left side, it gets closer and closer to that point where the y value, okay, if we'll extend that, so the y value is between 0 and 1, okay? So there's a certain value that is being approached by the function, okay? So it doesn't mean there's no limit, okay? There is a limit. It's just that it is not determined using this method on the left. Okay, so how do we get the limit if the limit is really defined? It's possible that the limit is not defined. Okay, meaning it goes beyond bound. No limit or it's limitless. Okay, but we cannot conclude that it has no limit. It's just that it's not determined using this method. So we need to do something with the given function. So if we look at the function, okay, we see, okay, let me zoom that in. So we can see some common factors or common factor. Okay, this is there is a relationship no, between x minus 1 and x squared minus 1. So from our algebra, okay, we have x squared minus 1, which is a difference of two squares. We can factor it out. Okay, so recall no, the factoring of difference of two squares. So we have x plus 1 and x minus 1 for the factors of x squared minus 1. Okay, so by factoring, so x minus 1 is, of course, no longer factorable, so just write it as it is. And then x squared minus 1, so let me rewrite the given here. And then do the factoring on the right side. Okay, for a moment. Okay, so we have, okay, if you are not yet applying the properties of limits, make sure that you write the limit notation. Okay, so we are not yet finding the limit. We are transforming the function first so that we can apply the properties. So make sure to write the complete notation. So you have x minus 1, and then x squared minus 1 can be written as x minus 1 times x plus 1. Okay, so there's a common factor. X minus 1 is a common factor. So take note that there's still a 1 above. So common mistake is students tend to disregard the 1, the remaining 1 na factor in the numerator, and just write it as x plus 1. In fact, this is not x plus 1. It's 1 over x plus 1. Okay, take note of that. So meaning limit of 1 over x plus 1 as x approaches 1. So we are now eliminating the common factor. So if we are going to get rid of x minus 1 in the numerator, then the numerator will not be equal to 0, right? And there will be no 0 also in the denominator because x minus 1 is being eliminated. So this no longer 0 over 0. Okay, so we can now find the limit. So there's really a definite limit for this given function. Okay, so using the properties, so we have limit of 1 as x approaches 1 is 1. And then limit of x as x approaches 1 is also 1. And then plus limit of 1 is also 1. So we have, okay, 1 over 2 or 1 half. So there is really a limit. Okay, so limit of x minus 1 all over x squared minus 1 as x approaches 1 is 1 half. So if we are going to look into the graph again, so it's actually midway between 0 and 1. So the limit is 1 half. Okay, so that's how you find the limit in indeterminate form. Okay, if it's in indeterminate form. So another example, okay, it's not always removing the common factor. So it depends on what function you're dealing with. So let's have another example. Okay, the limit of, okay, so um, let's say 1 over x minus 1 half. Q1, okay, 1 over x minus 1 half. And then for the bottom part, the denominator, let's say it's x minus 2. Okay, so let's not assume first that this is in indeterminate form. So we'll use the properties. Okay, so we have 1 over x. So get the limit of 1 over x. So it's 1 over, as x approaches 2. So we have 2 and then minus 1 half. So divided by 2 minus 2. So we get 0 over 0, or it's indeterminate. Okay, so we need to find a way to get rid of indeterminate. So find a way to eliminate the zeros, or at least one of the zeros. Okay. Pwede man na 0 over 1, which means 0. The limit is 0. It can be 1 over 0 or undefined, so meaning there's no limit. Okay. So I'll just continue here. Okay. So you can just put the solution for transforming the function into something that will not give 0 over 0. So since we are going to transform first the function, so you need to write the limit notation. Okay. So we have 1 over x minus 1 half. Okay, it has something to do with the x minus 2 below. Okay. So maybe we can combine the two fractions above, no, in the numerator. Okay, so let's combine them. So we have x and 2. Okay, so x and 2. So we're going to merge, no, the two fractions to just one fraction. So we get the LCD, okay, or the least common denominator. So least common denominator of x and 2 is 2x. Okay, so let me write first the main line. Okay, so 2x for the LCD, and then 2x, diba? The next step is to divide the LCD by the denominator of the first fraction, and then multiply it to the numerator of the first fraction. So 2x divided by x times 1, that's 2. Okay, and then minus 2x divided by 2 is x times 1, so that's x. Okay, and then just copy the denominator. So the next step is you try to find a common factor. So you can see we have 2 and x, 2 and x, but it's being swapped. Okay, but we can always multiply a number or an expression with any number as long as it's equivalent to 1. Okay, so we can transform 2 minus x into x minus 2 by multiplying it by -1, right? So we're going to multiply the numerator by -1. So it would result to -2 plus x, right? Or you can write it as x minus 2. Okay, which is equal to the denominator, na, x minus 2. So we can cancel out because they are common factors. Okay, so if we are multiplying the numerator by -1, make sure that you balance it. Okay, we cannot change the value of the fraction. Okay, make sure that what you are multiplying is equal to +1. It keeps the identity, okay, of the function. So if we're going to multiply the numerator by -1, so we also multiply the denominator by -1. So let me change the color. So we multiply with -1. Okay. So we are not changing the value of the fraction, right? So because -1 over -1 is just equal to +1. So no changes in the value of the fraction. Okay, so no need to distribute the negative 1 to x minus 2 because the purpose here is to get rid of a common factor. So let me just write the new form. Okay, so we can write the x minus 2 and then over to x and then all over, okay, let me rewrite, all over x minus 2 and then times negative 1. Okay, so let's just put the negative 1. We can put it on before the fraction, or let's just put it here first. Okay, and then we'll simplify the fraction later. So we now have a common factor. We can um, cancel out, okay, because when we, what do you call this? Simplify a complex fraction. So we multiply the reciprocal of the numerator or denominator, I mean, to the numerator. So if the numerator is x minus 2 over 2x, so multiplied by reciprocal of the denominator would be, okay, 1 over x minus 2 times negative 1. Okay, or just put the negative 1 na lang here above. Okay, over x minus 2. No? We can put the negative 1 either in the numerator or denominator. It's just the same. Okay, the fraction is still negative. So that's why we can cancel it out because common factor. Okay, so shortcut ana is na we can no cancel out the 2. Okay, don't just cancel anything. Make sure that you understand why you are canceling the expression. So again, this is the result of simplifying the complex fraction. Okay. So getting the reciprocal of the denominator and then multiplying it to the numerator. So the common factor is eliminated. So take note, there's still a 1 here on top. Okay. So we have, yes, actually 1 over 2x and then all over negative 1. Or we'll just put the negative sign before the fraction itself. Okay. So we have 1 over 2x. So negative 1 over 2x as x approaches 2. Okay. So since it's a negative fraction, so make sure to enclose with parentheses. So we can now apply the properties of the limits of a function. Let's see if we can get a limit already. Okay. Or let's proceed to the application of the properties. Okay. So it's negative 1. So by now I think you already have observed no, the pattern. Okay. Applying the properties simply is the same as plugging in no, the value that is being approached by x to the x in the given function. It's negative 1 over 2 no, times 2. Okay, or that's negative 1/4. Okay, so that's the limit of, again, rewrite given. So 1 over, what's that? 1 over x. Okay, minus 1/2. And then over x minus 2 as x approaches 2. Okay, so the limit is negative 1/4. All right, so that's all on the limits in indeterminate form. So up next would be the limits at infinity and infinite limits. So they are two different things. So goodbye and see you in the next topic.